A very good day to everyone. First of all, I would like to thank the organizers for inviting me to be a keynote for the International Conference on Advances in Construction Materials and Structures, ICCMS 2021. My name is Kim Han Mo, and I'm from the Department of Civil Engineering, University Malaya, Malaysia. The topic of my presentation today is on the performance of lightweight cementitious composite with hollow spheres. I'd like to acknowledge the works of my PhD student, Kyung Wen Leong, and also other students who are directly involved and also indirectly involved in the works that I will be presenting. A little bit background about myself. I'm presently senior lecturer in the University of Malaya, and prior to that, I did my postdoc in the same university after graduating from my PhD in the same university. I'm a professional engineer with the Board of Engineers Malaysia, as well as a chartered engineer with the Engineering Council UK. I'm categorized as the world's top 2% scientists, according to the research done by Stanford University for the single year 2019 as well as 2020. I currently have published in 100 journal articles, and these journal articles are all indexed in the Web of Science. And I currently have a H index of 29 according to the Web of Science. Right, so I'd like to start off with a brief introduction about the typical types of lightweight concrete. So the first type is this lightweight aggregate concrete. So the lightweight aggregate concrete is usually obtained by replacing part or the full amount of the aggregates with a lighter weight aggregates. And this kind of lightweight aggregates are usually porous and have high water absorption. And this may actually cause some properties to be decreased in the lightweight concrete. But nevertheless, in this kind of lightweight aggregate concrete, we can still get good amount of strength. But another issue is that the density reduction in this kind of lightweight concrete is usually also limited, where we cannot really reduce it to a very, very low density. On the other hand, the second type of lightweight concrete, which is this aerated or foam concrete. So this kind of lightweight concrete is, we usually can get a very low density, right? And this kind of aerated or foam concrete is done by introducing air voids or air bubbles into the concrete. We can get a very low density with this kind of concrete. But in these cases, when the density is very low, it means that we are actually using high amount of, we are putting in high amounts of voids or air bubbles. And this may cause the coalescence of the bubbles or the voids, which in turn may actually reduce the strength substantially and cause the foam concrete to have low strength and therefore low durability. So a third type of lightweight concrete is the no-fines concrete, or we also call this as a pervious concrete. So this typically involves taking out the fine aggregate portion of the concrete. Usually this is only designed for water permeability and also for non-structural purpose. So in short, the common types of lightweight concrete has certain limitations, right? And one of it is the limited density reduction. You can't really reduce the density substantially. This is in the case of the lightweight aggregate concrete. And also we have the limitations of significantly low strength and also durability when we try to reduce the density to be very low. So this is the case of the aerated or the foam concrete. So this leads us to consider the use of lightweight fillers, right, in the form of hollow sphere. So the two types of hollow sphere that we consider is the Perlite microsphere as well as the fly ash sphere. So this type of hollow sphere, because it has essentially a high amount of air voids in the internal structure of the particles, so the bulk density you can see is very low. Okay, but in this kind of hollow sphere, they are encapsulated by a thick and strong outer shell. So it gives a certain amount of crushing strength to the hollow sphere itself. And at the same time, the water absorption of this type of hollow sphere are also much lower than conventional lightweight aggregates. And the size of this hollow sphere are usually about 100 to 200 micrometer. So the idea of using this hollow sphere is to make use of its very low density, so which can bring down the overall density of your concrete, and as well as the high crushing strength of the material, the hollow sphere itself, so which may help to retain a certain portion of strength even when the density is substantially reduced. So therefore, we want to introduce this hollow sphere lightweight fillers and try to see the effect or the performance of the resulting lightweight cementitious composite. So we first tried off with getting a very low density lightweight cementitious composite using the Perlite microsphere. So you can see from here, we are targeting a density within the range of 800 to 1,200 kg per cubic meter. So in these cases, we are basically looking at the lightweight fillers of the hollow sphere Perlite microsphere. We are using it as, we are basically modifying the ratios with the binder and also with the water, but we are not using any fine aggregate in this case. So as you can see, we tried out with 3 different binder contents. So when we have a lower binder content, so obviously the lightweight filler or this Perlite microsphere content is going to be higher. So when we actually look at these different binder contents, the lower the binder content, we can get a lower density. Okay, and the density, the lowest density that we can achieve over here is about 800 to 900 kg per cubic meter. And with this density, we can actually get a compressive strength of about 10 MPa and a flexural strength of close to 2 MPa. So to put this into perspective, if you're looking at in the literature, some of the density concretes, lightweight concretes with a similar range of density, so mostly is on foam concrete as well as lightweight concrete. The density with this range, the strengths are usually, you can see from here, mostly lower than 10 MPa, right? So the this Perlite microsphere LCC, the specific strengths of it, or simply we call it the strength over the density ratio, is much higher than the other types of lightweight concretes, okay, especially in this range of density. So when we actually have a slightly higher binder content of 600 and 720 kg per cubic meter, as you can see from here, right? So the compressive strength can exceed even 20 MPa, and the flexural strength can be close to 3 MPa. And this is when the density is around 1,000 to 1,200 kg per cubic meter. So there should be a certain threshold where this kind of hollow sphere can be used to a stage that a more substantial reduction in strength will be observed. Okay, so we think that is about 1,000 kg per cubic meter of density would be most ideal, because we still can get good amount of strength that is above 20 MPa, and the density is, of course, we maintain it around 1,000. So then we also tried out, because we have to maintain the density at about 1,000 kg per cubic meter. So we tried out also to use the air entraining agent to bring down the density, and also to check on the insulation, sound insulation properties of this Perlite microsphere LCC. So when we increase the air entraining dosage up to 1%, the compressive strength, we can see a quite substantial decrease from about 15 MPa down to about 5 MPa, even though the density is reduced from 1000 to 800 kg per cubic meter. But nevertheless, the insulation properties can actually be substantially improved when we use this air entraining admixtures. Similar as most commonly available lightweight concretes, the brittleness of lightweight concretes is also an issue, or rather a consideration. So therefore, we try out the use of fibers to improve the mechanical strength of the Perlite microsphere LCC. So because when we did this Perlite microsphere LCC, the density are also at the lower range. So therefore, the brittleness is also going to be our consideration. So we tried out the PP fibers and also the PVA fibers. So when we first tried out these PP fibers in our Perlite microsphere LCC with the 3 different ratios that have a binder content of 420, 600, and 720, the compressive strength is not very obviously affected with the PP fibers, and there's also only marginal improvement in the flexural strength when we use the PP fibers up to 0.5%. So then we compare the use of our PP fibers with the PVA fibers. And obviously, when we use the PVA fibers up to 0.5%, there's a more obvious increase in the compressive strength and also the flexural strength. So the PVA fibers, we believe that more than this 0.5% will be beneficial for improving the mechanical strengths and reducing the brittleness of this kind of Perlite microsphere LCC. So then we, of course, with normal lightweight concrete, one of the concerns is also the high amount of water absorption, because in normal lightweight concrete, we have lightweight aggregates that have high water absorption. But of course, in the case of Perlite microsphere, the water absorption of the hollow sphere itself is not high. Okay, therefore we can see that when we measure the water absorption of the Perlite microsphere LCC after 48 hours, the water absorption is only about 15%. So this is almost similar as a normal concrete, a normal grade 20 concrete, right? Then we thought of trying to further reduce this, just to ensure that this Perlite microsphere LCC has much better water resistance. So we included the waterproofing admixture. Right, we dose it at 1% and 2%, and we find that the water absorption actually substantially reduced when we use 1% and 2% of this waterproofing admixture. Then we also look at the hydrophobicity of this LCC with the inclusion of waterproofing admixture. So when we put in 1% of this waterproofing admixture, the water contact angle actually increases from around 96 to 130. So at 130, so this angle is actually considered quite a high hydrophobicity. And this is actually going to be helpful for the Perlite microsphere LCC in terms of the water resistance. But when we put in 2% of waterproofing admixture, the water contact angle actually reduces slightly. So therefore, we concluded that this 1% waterproofing admixture is optimum for the fiber added by Perlite microsphere LCC. And importantly, because of this waterproofing admixture, we can improve the water resistance of the LCC, right? Because commonly in lightweight materials, the wet compressive strength of concrete will usually be much lower than the dry compressive strength, and the lower is this ratio means that it is less water resistance. So when we actually put in the 1% waterproofing admixture. So this ratio actually increases from 0.5 to 0.85. So it significantly improved the water resistance of the Perlite microsphere LCC. So those were the studies that we actually studied on the properties of Perlite microsphere LCC without the use of any sand. We basically try to reduce the density and to achieve a good enough strength. Then we move on to comparing the effect of different types of hollow sphere. Right, we compare the use of this Perlite microsphere with the fly ash cyanosphere. But in this case, we are using the two hollow sphere as a sand replacement to get the LCC, to get the lightweight cementitious composite. So we increase the sand replacement amount from 0% to 100%, right? And in this case, you can see obviously for the use of both Perlite microsphere and the fly ash cyanosphere, the densities are basically reduced in quite a linear trend. And with the 100% sand replacement with the hollow sphere, the density can go to as low as about 1,300 kg per cubic meter, right? And of course, in this case, the porosity will be increased at the same time. Okay, when we put in more of this hollow sphere, because of the hollow structure and the air contains inside of the aggregate of the hollow sphere itself, so this actually increases the porosity and therefore reduces the overall density. But interestingly, we can see even when we increase the replacement of sand with the hollow sphere from 0% to 100%, naturally the density will be reduced. The density is actually reduced by more than half of it, around half of it, from 2,100 to about 1,200 kg per cubic meter. But we can see that the compressive strength is still fairly good, even at its lowest density of around 1,300 kg per cubic meter. So the compressive strength is exceeding 30 MPa at least, and at such a low density, a 30 MPa compressive strength is actually considered quite good, right? Quite high. And it can be even considered as a structural grade with this compressive strength. And when we actually compare the two different kinds of hollow sphere, obviously the one with using fly ash cyanosphere with the orange line, so these are higher than the LCC using the Perlite microsphere at a given sand replacement level. So this is because in the fly ash cyanosphere, the material itself has a thick shell, much thicker shell compared to the Perlite microsphere. So this actually gives a higher crushing strength to the fly ash cyanosphere itself. And because of this, when the cracks actually passes through the aggregate or the hollow sphere of the fly ash cyanosphere, so this thicker shell can actually impart strength, okay, and also retain certain amount of strength compared to the case of the LCC with the Perlite microsphere. The crack is actually surrounding the Perlite microsphere. And we also believe that because there are also certain amount of some reactions of the fly ash cyanosphere, because it is also a pozzolanic, considered a pozzolanic material. So there are formations of CSH around the shells, and this actually is may also be one of the factors that improves the strength, because it actually improves the interfacial transition zone. And therefore, when the crack actually passes, and this actually causes the crack to pass through the hollow sphere instead of around it. So therefore, these are the reasons that the fly ash cyanosphere LCC has higher strength than the LCC using the Perlite microsphere. So when we look at the literature, the range of similar densities with a given compressive strength, so the Perlite microsphere LCC and also the fly ash cyanosphere LCC, the specific strengths of it, or as mentioned before, the compressive strength over the density ratio is over on the higher side. Okay, so the red crosses are basically the results from here, which actually are on the higher side. And interestingly, when we look at the water absorption of this material, so as mentioned before, the water absorption of lightweight materials are usually an important consideration, because for normal lightweight concrete, it is usually quite high. But in this case, we can see that when we utilize perlite microsphere and also fly ash cyanosphere as a replacement of the sand, the water absorption would not be substantially increased for the case of perlite microsphere. And in fact, at 100% replacement, the water absorption actually reduces. And for the case of fly ash cyanosphere, using the fly ash cyanosphere itself will essentially reduce the water absorption of the LCC. And the reason for this is because when we use this kind of hollow sphere, and because of the particle size, which is about 100 to 200 microns, so this actually can provide good particle packing, and which can actually fit in the voids left very well. So so we can see an illustration without a fly ash cyanosphere. So there are voids available in the matrix, okay. But when we include this lightweight fly ash cyanosphere, because of the finer sizes of this hollow sphere, it can actually fill in the voids, and this actually helps to reduce the water absorption. Okay. So when we also can see from the SEM images, so without any fly ash cyanosphere, you can see that the sizes of the voids are rather large. But when we included the fly ash cyanosphere, so some of the voids are actually filled up with the fly ash cyanosphere itself. All right, and because of this, the water absorption is reduced. And at the same time, because of very low density of the fly ash cyanosphere itself, filling in these voids will also not substantially increase the density of the LCC. So the fly ash cyanosphere gives the best packing basically at 75%, and we use it to replace the silica sand. And we also look at some of the other properties of the perlite microsphere LCC as well as the fly ash cyanosphere LCC. So naturally, when there are increasing amounts of this hollow sphere, the thermal conductivity is decreased, thermal diffusivity is also decreased. This is actually going to be better for thermal insulation. And the range of the thermal conductivity is also very well fitted to what we find from the literature. So we can see there are different references that we compare the effects of the use of lightweight materials with different densities and the corresponding thermal conductivities. So it fits very well into the normal range. Okay, but of course, one of the issues with lightweight materials is always also on the shrinkage of the materials, and because usually the aggregates portion are the one that is providing restraint against shrinkages, and therefore in this case, when we're using this kind of hollow sphere, the shrinkages are usually higher, especially when you're replacing higher amounts of sand. You can see that the shrinkage are all increasing. So therefore, this is also one of the reasons that we tried on with adding fibers. Okay, and in this subsequent works, we try out the use of fibers into the fly ash cyanosphere LCC. So we just did something on the mechanical strength. we compare the use of PVA fiber and basalt fibers up to 0.75%. And we can see that the basalt fibers at below 0.5%, the performance is okay. It gives good performance, but when we increase it to 0.75%, we can see drops in the mechanical strength. So this shows that the basalt fiber, we can't really include high amounts of it because it might be more difficult to mix because of the high stiffness of it. But when we look at the PVA fibers, the trend is showing that the compressive and also the flexural strength can actually be still improve when we use higher amounts of the fibers. So therefore, then we incorporated 1% of the PVA fibers instead into our fly ash cyanosphere. So we can see the this column in this table that is with the black highlighted box over here. So the importantly, when we use 1% of PVA fibers, the compressive strength can be substantially increased, right? More than 10% of increase, and the flexural strength is almost double. And the splitting tensile strength is also having a substantial increase. So the use of the 1% PVA fibers is actually going to help in improving the mechanical performance. And of course, when we deal with lightweight concretes, as commonly, the binder content is usually much higher than normal concrete. And because of this, we have issues when cement content is too high. So in this case, we also tried out with a high amount of cement replacement with GGBS. So we actually use 50% GGBS, and we also tried out with 10% silica film. So I'll just highlight the results of the fly ash cyanosphere that is replaced with 50%, that the cement is replaced with 50% of GGBS. And this also have the 1% of PVA fibers. So in overall, we can see, comparing all of the properties, the mechanical properties over here, there is hardly any changes in it, despite the GGBS is used as a 50% cement replacement. So this is good where we can use lesser amount of cement and to actually get a more eco-friendly kind of LCC. So at the same time, the thermal conductivity is still largely unaffected, even when we included the fibers, and also even when we use up to 50% of GGBS. So then we move on into trying to further reinforce this fly ash cyanosphere LCC, not only with the use of PVA fibers. We also want to see what are the effects when we use textile fiber mesh. So in particular, we are using this glass fiber textile mesh. Okay, so we end up with a textile fiber reinforced fly ash cyanosphere LCC. So we tried out with, so in this case, we tried out with two different number of layers of the fiber mesh. We try with 2 layers and also 4 layers, and we make a comparison. With normal textile reinforced mortar, and we also make a comparison with fiber reinforced lightweight cementitious composite without the mesh. And the results are shown as here. So in the control, the control over here, we are using a normal cement mortar, and we are using 4 layers of mesh. And the second one over here is where we use the fly ash cyanosphere lightweight cementitious composite, and including the 1% of the PVA fibers. So we can see that when we use our fly ash cyanosphere LCC, even when we put in this 1% PVA fibers, in terms of the ductility, the toughness is similar as the normal textile reinforced mortar. Okay, but when we use this fly ash cyanosphere LCC without any fibers, and it's only reinforced with 4 layers of textile mesh, the one highlighted in dark blue over here. When we compare the flexural strength with a normal textile reinforced mortar, it is also similar, and the toughness is also similar. So it means that in a textile reinforced system, if we use this fly ash cyanosphere LCC, it will give a similar performance as a normal textile reinforced mortar using a normal cement mortar, right? And if we further look at this row of results with the light highlighted in light blue, so this is a fly ash cyanosphere with the 1% PVA fibers, but with only 2 layers of glass fiber mesh. So essentially, we are, instead of using 4-layer mesh, we tried out with using 2-layer mesh, but we included 1% of the PVA fibers in our fly ash cyanosphere LCC. And interestingly, if we compare with the results for the fly ash cyanosphere LCC without any fibers, okay, the flexural strength is already increased, even we use less number of mesh, and the toughness is also much more significantly increased. So this means that when we use lesser number of mesh, but with the presence of fibers, there are some synergistic effect which can help to improve the overall flexural performance of this textile reinforced fly ash cyanosphere LCC. So when we increase the number of mesh to 4 layers for our fly ash cyanosphere LCC with the PVA fibers, so these are the 2 that are highlighted in red. So one of it is using only cement, and the other one is with 50% GGBS. What we can see is that the presence of the additional 2 more layers of mesh compared to the one with highlighted in light blue, you can see that the flexural strength is substantially increased now, and the toughness is also almost double. So here we can see that obviously in this kind of fly ash cyanosphere LCC, when we included 1% of PVA fibers, and if we include 4 layers of mesh, it gives a very substantial improvement to the tensile or the flexural properties. If we compare back to the original normal textile reinforced mortar, right, we can see that the toughness and also the flexural strength is substantially improved, even when we are using just this kind of lightweight cementitious composite, which have a lower density. But the overall ductility can be improved through the use of PVA fibers in combination with the glass fiber mesh. So when we look at the failure mode of the specimens, so in the fly ash cyanosphere containing PVA fibers, the first one over here, and without any mesh, you can see that there are only a few crack lines. These are mostly concentrated at the center. When we subject this when we subject this composite under flexural load, and so the main contribution in resisting the tensile cracks or the flexural cracks are because of the fibers only. But even with only the fibers, we can see multiple cracking still exist. So it means that the 1% PVA fibers actually can already overcome the brittleness of the fly ash cyanosphere LCC. And on the other hand, if we just reinforce our fly ash cyanosphere LCC with 4 layers of textile mesh, all right, without the use of any fibers, so the number of cracks are actually much less, and there are a dominant flexural crack line. So therefore, this type of so when you're only using the glass fiber mesh to reinforce the LCC, it would not be giving good enough ductility. So therefore, the use of the fibers in combination with the mesh is going to be required. So when we actually do so, we use 2 layers of mesh and we also use 4 layers of mesh, what we can see is that the number of crack lines actually increases and is extending to a wider region. So there is combined effects that actually help to improve the overall flexural performance and ductility of this fly ash cyanosphere LCC. And this is much more obvious when we put in 4 layers of mesh, and together with the PVA fibers, you can see that there are multiple crack lines, which is much more obvious. So these multiple crack lines actually suggest that there could be strain hardening in this textile reinforced fiber LCC. All right. So if we look at the top picture over here, so it shows that the effect of adding in the glass fiber mesh, right? Without any glass fiber mesh, there will still be a little bit of ductility due to the use of 1% PVA fibers. So definitely in this kind of like fly ash cyanosphere LCC, we will still require the use of at least fibers to make sure that it has sufficient ductility. But when we include 2 layers of mesh and 4 layers of mesh, we can see that there's much more strain hardening, right? The specimen can actually undergo much more deflection at a given load, right? So this shows the effect of the positive effects of also adding in an additional fiber mesh layer. So so you might wonder why we do not actually want to just increase the amount of fibers instead. So the reason we are not doing this is because it is usually much more harder to incorporate high amounts of fibers, let's say to 2% or 3%, and that might involve adjusting the mix, and which might require much more binder content, and in turn this actually increases back the density of your material. So therefore, instead of including in more discrete or individual fibers, we combine this with the use of a textile mesh that is placed along together with the LCC. So when we compare the effect of cement replacement material, because earlier on we investigated what is the effect when we put in 50% GGBS and 10% silica fume. So we can see that obviously there is not much difference in terms of affecting the ductility. The orange color line is for the 50% GGBS replacement. So the strain hardening is still there despite replacing much of the cement. And we can also see the yellow color line is the fly ash cyanosphere LCC with only the mesh, which is not going to be ductile enough. You can see significant drops of the load. So when we look at the failure mode, if we just use textile mesh to reinforce the LCC, so upon failure it's just a single crack and it just snaps into 2. But with the use of with inclusion of the PVA fibers with the textile reinforced mesh, we can see that it's a more gradual failure and the fibers are all pulled out instead of a very clear break like what we see for the samples without any fibers. So when we look at the SEM images, we can see that the materials are well bonded. Okay, in the glass fiber mesh, you can see hydration products attached to the textile mesh. This is the SEM on the right side. And we look at the SEM on the left side, we can see that this is the layer of the mesh here and here. So when we have these 2 layers of mesh, of course, in between this mesh, it is the LCC itself. So when we have fibers in our LCC, so the fibers can act as joining, as joining the meshes together in the parts, separating it, so that it forms a network of reinforcement that can actually help to more effectively improve the flexural performance. Because normally when we do not have any fibers in between, then the reinforcing is just by each layer of mesh. And when one of the layers fail, then the crack will just propagate through and taken by the next mesh directly. But with the use of fibers, it can delay the failure of the portion in between the meshes, and that is the one giving more ductility to the composite. So in conclusion, what we can get from this research is that the hollow sphere, we are using this hollow sphere lightweight filler. We can use it to produce LCC with low density. So it depends on the density that you're targeting. It can go below 1000 kg per cubic meter, or it can be slightly above 1000 kg per cubic meter, but still having very good strength. And it also has good insulation properties such as sound absorption and also the low thermal conductivity. And also importantly, it will have a much lower water absorption compared to conventional lightweight concretes. So this is actually important to ensure that the LCC has good durability. When we compare the two different kind of hollow sphere, the fly ash cyanosphere actually performs better than the Perlite microsphere. The fly ash cyanosphere essentially has a better crushing strength, and also because it has some pozzolanic reaction, so this actually helps to improve the performance. Introducing the 1% PVA fibers can already substantially improve the mechanical properties and also a little bit on the ductilities. But to further improve this without using even more fibers, so we combine this with the use of textile mesh, and we find out that when we use 2-layer and 4 layers of mesh together with the LCC with the PVA fibers, the overall flexural performance, the ductility is much improved. We can even get strain hardening. And this will be particularly useful if we are using it for thin applications, right? Because the textile reinforced systems are usually for thin layer applications or thin structures. So with that, I conclude my presentations for today. Thank you very much. My contact email is there. If you have any questions, you can drop me an email. So my apologies for not being able to join the conference live, right, due to other commitments, but I always welcome if you have any questions, you can directly email me regarding the presentation or any other things, right? With that, thank you very much, and that's all for my presentation.